You're all set.
Hello, everyone. I am Shefali and welcome to my session on kernel tracing. So I am a senior year computer science student from India at ELISA Medical Devices Working Group under the Linux Foundation Mentorship Program. So I will be today discussing some tools that are very helpful for tracing and analyzing the kernel. So I will be discussing today Strace, ftrace, Cscope, and perf. Before going further, I would like to thank my mentors, Shua ma'am and Milan sir, for believing in me and giving me this opportunity for their stimulating suggestions and unending support. I am also very grateful to all the members of the Medical Devices Working Group, to Kate ma'am, Nicole ma'am, Jason sir, and Jeffrey sir for their constant guidance and support. In the end, I would like to thank Linux Foundation for providing me this platform. So I would like to start this discussion with system calls. So if a user space application like Chrome wants to access any kernel or hardware resource, then it has to issue system calls. User space applications don't have the permission to directly access the hardware resources. So in order to use the hardware resources, the user space programs have to make system calls to the kernel, and then the kernel services their request. So the only way user space applications to use these resources like file system, memory, is by with the help of system calls. So broadly speaking, there are two modes in an operating system. So first is user mode. It has restricted control over the hardware. In order to use any system resources, it has to issue system calls. And second is kernel mode. It has full control over the hardware and it can execute any instruction and access any memory location. So some examples of system calls are create. It creates a new file and assigns it a file descriptor. So file descriptor is a unique identifier for a file or any other input-output resource. And pipes, they create a channel for inter-process communication between two processes. And ioctl, they are used for controlling a device. And socket, they are used for creating a channel for communication over the network, and it returns a descriptor. And memory map, it establishes a mapping between the processes address space in the RAM and a file on a disk. So one question that may come to your mind is, what are the advantages of this approach? So system calls allow the kernel to carefully expose these pieces of functionality to user space programs. For example, if some file is only accessible to the root user, and if some other user is able to access that file by directly reading it, so then there is no point of having that file. So having system calls, a system like this, it helps to improve the security and the safety of the system. And secondly, it results in less coupling between the user space applications and operating system. So it is easy for application developers to make portable applications without keeping in mind the hardware or system architecture. So I will be discussing Strace tool now. So what it does is, it is a very useful tool and it prints out the system calls that are made by a program. So very useful for debugging and overall a very useful tool. So this is how it works. It works on any command. We have to just Strace and then insert the command name. So these are all the system calls that are made by a process. And so these are, there are many file system calls that you can find. And I can show also if I do. So here you can find many network related system calls. I did it over ping command. So that's how it does. You can also create a very nice report for all these system calls using Strace by using the -c parameter. It prints the total time they take, and total time and number of calls and errors also they display, and they display the system call names. And verbose mode, it gives more detailed information about the system calls made. All this information that you see here, it was not shown in the previous command. And here they give more detailed information. So one question that may come to your mind is that what problems can be solved using Strace? So we can use Strace to see how a process interacts with the kernel. So to see why a process is failing or hanging as it receives it displays all the signals it receives from the kernel. So very useful for debugging purpose. So if you don't know the source code of an application, then you can reverse engineer it using Strace. You can see how it works by seeing how it interacts with the kernel. So for reverse engineering, it is very useful. And this one is very useful to find the files on which a program depends. So we can easily find out that what are the necessary things that are required for a program to run. And we can see the arguments that are being passed to each system call. And we can troubleshoot various problems related to the operating system. Sometimes that the messages we get after a program failure, they are not very helpful. So we can use Strace to directly see what is causing that error. So the next tool that I will be discussing is Cscope. Cscope is a command line tool which is used for browsing C, C++, or Java code bases. It can be used for finding all the references to a symbol, global definitions, functions called by a function, functions calling a function, text strings, regular expressions, and files including a file. Overall, it is a very useful tool for understanding a code base, for understanding the flow of execution of various functions. So now I will be showing how we can use Cscope to find which system call belongs to which subsystem. So this way we can find the kernel subsystems used by a process when it is executed. So for that, you will have to first clone the Linux kernel repo. Then you have to build the Cscope database in it. So this is how the Cscope, when you will build the database, then you will get this console. So at the down, you have these options where you can enter what you want to find, and the output will be displayed in the upper section here. So in the kernel, all the Linux system calls are defined using the syscall defined regular expression in macro. So we can search for this regular expression and we will find this very nice output, and it will display all the subsystems where each system calls lie. So here are many memory related system calls in the memory subsystem. And over here, you can see the number also. It means that when I took this photo, there were 818 system calls supported by the kernel. So that's how I found the subsystems in which each system call lies. So now I will be taking a couple of workloads and show how we can determine the subsystems they use using Cscope and Strace. So first workload I will be generating using StraceNG. So StraceNG is used for performing stress testing on the kernel. It is very widely used to improve the kernel code. In the Linux kernel mailing list, you can find many examples of it. So it allows you to exercise various physical subsystems of the computer using stresses. They are available for CPU, CPU cache, network file system operators, operating system, etc. And it attempts to crash the kernel by exercising these stresses over them. And it aims to test the robustness of the kernel under very extreme conditions. So for Debian-based operating systems, this is the installation. So I will generate a workload using the netdev stressor. So it will start some workers and they will exercise various netdevice IOTL commands on them. So this way we can test the effectiveness of the network devices on this sample workload using the sample workload. So this is how it works, and it generates some metrics also. So I executed this stressor under Strace and gathered statistics for it. So these are all the system calls that it made. And I use Cscope to map those system calls to their subsystems. So over here, I can find many file system calls, memory management, signal process management, and network and time and few text system calls. So this was how we can determine the subsystem usage for a sample workload. I generated the next workload using Okay. So any questions? So I ran this workload under Strace, and these are the system calls that it generated. And I mapped those system calls using Cscope, and I found that there were many file system related system calls of signal subsystem. I found of time subsystem, of memory management and process management. So that's Strace, which is a very useful tool. It can be used to discover the system resources in use by a workload. Understanding the path that a workload is taking in the kernel, understanding the system resources it is using is important to avoid regressions and to evaluate safety considerations. This was our conclusion after running this workload. Another thing that we should keep in mind is that when we run a workload, there are many possible paths or methods that it can take. So depending upon some environmental conditions or many factors, the workload can take many different paths. So, so this method of tracing does not include all the possible system calls that can be invoked. Example, if a workload opens a file and reads from it successfully, then that path will be traced. Any path that the same system call may encounter under different circumstances will not be traced. So if there is a workload that provides full coverage, the method outlined here will trace and find all the possible code paths. So the completeness of the system usage information depends on the completeness of coverage of a workload. So this was our conclusion. So next tool that I would like to discuss is ftrace. Ftrace is a very useful tool for tracing kernel function calls, for understanding how the kernel works and how it handles various events. So ftrace, it is very widely used by system developers to find out what is going on inside the kernel. And the API to interface with ftrace is located in the Debugfs file system. which is automatically can be found in various distributions.
Shefali?
Yeah.
Okay, well, sorry, we just couldn't hear you for a little bit. We just wanted to make sure you're still there. Thank you.
Thank you. So I am going to the FRACE subsystem. It is a pseudo file system, and it can be used to see what is going on inside the function. It helps us to you have to be a root user if you want to use it. Otherwise, you cannot. So to use FTrace, you have to manipulate these files in order to control FTrace. If you want to see all the functions that are available for tracing, then this is the file you should refer. It contains all the functions that the kernel is composed of. And the modules, kernel modules that you write, they are also exported to this file system. So you can analyze your kernel modules also. So trace, it is the file that shows the output of an FTrace trace. And to turn on tracing, you should echo 1 to the tracing on file. And available traces, it is the list of traces that have been compiled into the kernel. And available filter functions, I just showed you. These are all the functions, kernel functions that are available for tracing. And available events are all the events available for tracing. I will discuss later what they are. Function, it traces the entry of kernel functions, and function graph traces both the entry and exit of kernel functions, and provides the ability to draw a graph of function calls. So they provide very insightful data about the function calls that are being executed in the kernel. And then there is block tracer for tracing iBio devices, and MMIO tracer, it traces the interaction between drivers and hardware. So in order to set the tracer, you should echo the tracer name to the current tracer file. So this slide shows how you can gather a sample trace from the system. So to turn on tracing, you have to echo 1 to tracing on file, then echo function. Then you have to specify the tracer name that you want your tracer to be. And then to turn off tracing, you have to echo 0 to tracing on. And then this data will be generated. So this shows all the function, all the kernel functions that were executing when the tracing was on. So this is the process ID of the process. This is the CPU on which it was executing. This is the time when it was executing. And this is the name of the function that was executing. And on the corner, this is the name of the function that was calling this function. So I will show you one sample trace. I will show you function graph trace. So first you will have to turn on tracing. now you have to echo the current into current tracer, the tracer you want to work with. Now I am stopping tracing. So now let's see the trace that we have gathered. So these are all the function calls. The function graph, it traces both the entry point and exit point of the function, whereas the function tracer, it was only tracing the entry of the function. So it is also showing you the duration for which the function ran. So this way you can troubleshoot the latencies of the system. So overall, it is a very nice tool to understand how the kernel works, to understand how an event is handled by the kernel. So we can use filters also. We can specify a string that we want to trace. And it will, for example, I specified the VFS string in the set if trace filter, and it showed me results regarding the functions that had VFS in it. And similarly, we can trace functions only of a specific module, that be INS mod or any other module. If we want to trace only those functions that are calling only those functions we want to specify, and all the functions that they call, then we have to use set graph function file. So if I use the previous file, then it traced only the functions that contained that string in that file. Now it is calling all the other functions that file is calling. So throughout the kernel, there are hundreds of starter points. Now I am discussing about event tracing within the kernel, and when they hook to a running kernel at the point, they collect very useful information. So this information is used by many tools also, which for debugging and performance tuning. So these are all the events that can be found. There are two ways to enable events. There is one directory. There is enable directory of every event. So if I do then you will find an enable directory in every event. So to turn on an event, you have to echo 1 to it. But there is another way also. There is one file set event. So there is the syntax. To see what it is, we have to read that in the set event file. The events file, it contains all the event tracers that are available. So in this, and we have to use set event file to enable a tracer. So I used sketch switch event, and it retrieves information from the scheduler, and it gives information about the processes that are being switched out and switched in by the scheduler. And next is trace command. It is a command line tool, and it provides a layer of abstraction over its trace. And this is an example. You can run it in your free time. Uh, it, uh, it traces all the functions that are called by a particular process. So it is easier to use. And there is a kernel track also. It is a GUI tool. So you can try that. And I have discussed already the uses of Strace for collecting the data, and it is very useful for tracing embedded systems in BusyBox environment that So next is perf. So it is a very useful profiling and monitoring CPU profiling tool for monitoring CPU performance on Linux systems. So it is based on perf events interface. It is a system call that is used for accessing the performance monitoring unit, which gathers very useful information from CPUs and other things and memory. So very useful tool overall for profiling and analyzing the performance of an application. So in order to install the sorry, in order to install the latest version of perf, you have to clone the Linux repo and compile it, and then you have to navigate to the tools/perf directory and compile it. So statistics command, it is a very useful command. It generates a report of various hardware, software, and trace points, so events. So this is how it is used. Perf stat, the command you want to analyze, and perf list and perf stat. And next is perf top. So over here, you can see different kernel functions. There is top command also. It analyzes only the processes and threads, but perf top, it analyzes kernel functions. So these are both all types of functions kernel also. A means that it is a kernel function. So if you press A on any function, uh, you have to use perf annotate to do that. Here also we can do it. And we can do repeated measurement also to and get the standard deviation from mean for each measurement. And top I recently discussed. And it records the data in perf.data file. And to read perf.data, we have to use a report. And we can use annotate to see the annotated code. So this way, we can narrow down our focus area. It provides very useful insights. So we can narrow down our focus area and see which code section is causing most latencies. And we can optimize that to optimize the overall performance of the application. So call graph, it shows you the CPU stack trace. And I executed the perf bench workload and to determine the system calls it is using. So perf bench, it is used for exercising and helps to evaluate the performance under various benchmarks. And it is overall a very useful tool for mitigating performance regressions. So this is how it looks when it is executed. And when I executed it under Strace, these all system calls it was calling. And these were the subsystems when I mapped it using Cscope. So the conclusion is that understanding system resources necessary to build a workload is very important. And Strace can help us to do that. And the completeness of the system usage information depends on the completeness of coverage of a workload. And Strace perf Strace NG packs test They are very important tools for the security of operating systems. And when we discover and understand what the workload needs, we can focus on them to avoid regressions and use it for safety analysis. So overall, my mentorship experience also, it helped me to learn a lot about the kernel. And my mentors also were very nice. They were always ready to help me and guide me in spite of their busy schedule. And I learned many things. And I learned about STP analysis, and I wrote a white paper, which is available on GitHub. So there is no time for questions. You can email to me any questions if you have. Feel free to email them to me. And thank you for being patient listeners. I hope that the session was informative. Thank you. Thank you.
Thank you for Shefali. Don't see any questions in the chat. There are
Yeah, you can email.